Very good. All right, so I'm receiving a final project abstract so I can see them all as soon as possible, and I'll approve them or give you feedback on them by tomorrow, and you can adjust from there, okay? All righty. So, let's see, we're kind of in the last chapter of the semester's subject matter. For the first half, basically, of the semester, we talked about coherent control of matter. We talked about Rabi oscillations, and we talked about adiabatic evolution and the like, and we talked about what we call coherence in matter, where we treated the light in those description as a classical field, okay? And we ignored any of the quantum nature of the field in our description. In this last, third class of the semester, we talked about the field itself. We talked about the nature of the electromagnetic field as a quantum field, particularly at low energies. We were interested in the optical regime or below. We're just talking about antenna, microwave antennas got photons too. We talked about the quantum nature of the field. So now what we want to do is put together, and we want to talk about atom-matter interaction. Okay? And of course that's, in particular, you know, in terms of regular matter, that's the study of quantum electrodynamics, right? QED is the study of the quantum theory of electrons and photons and positrons if we're at high enough energies, and we haven't ever thinking about antiparticles too, okay? So we want to talk about this now in the low energy regime, where we're thinking about particularly light, or we could be thinking about microwaves and its interaction with matter. In particular, the particular matter that we are in, I meant atom field, sorry, what I meant to say is matter field interactions. So we're particularly being interested in atoms, okay? I mean, when I say atoms, I mean this in a kind of more general sense as a material with well-defined bound states, discrete energy levels, like we might have in an atom, or in a molecule, or in a quantum dot, or in a transmon. We'll talk about, you know, various sort of artificial atoms that were created, or you know, and a defect in an ND center in a solid. We can think about that as a kind of atom. All right. So let's just, we can write down, and so particularly we're interested in this in the non-relativistic case where the matter is not moving relatively fast and the photons have relatively low energy. And if we were to write down sort of the most general Hamiltonian for that, where we have a bunch of charges, you know, we can write that as, okay, the minimum coupling Hamiltonian is 1/2 the sum of this guy, 1/2m, the kinetic momentum, which is the canonical momentum, minus the charges, these are the electrons, the vector potential at the position of the electrons squared plus the potential energy. This is what's known as the minimum coupling Hamiltonian. Mm-hmm.
Is that P a field, or should it have a J?
This is the momentum of the Jth particle. Yes. Okay, the Jth electron. Yeah. Right. And so this is the field of the atom and the atom interacting with the field, but we also should be quantizing the field, and that's the Hamiltonian field. The Hamiltonian field when we write this in terms of the modes, this is the sum over all the modes. Let's say if we think about those plane wave modes. Of course, I should also include the 0-point energy, but as we've discussed, the 0-point energy plays no role in the dynamics, and we don't include it. Yeah, no.
So are we assuming that we've gone back and quantized the field with
Yep.
A, or, okay, so we're not
Yep.
just cross-producting E and D?
Yep, everything well, no, like right, this is the most general Hamiltonian, okay? I'm gonna go back and say, what we're interested in, I mean, generally, yes, there is a quantum field description of the vector potential and the scalar potential and the like. This is the most general Hamiltonian I would write down, okay, in this context. Okay. Now, when we have something like an atom and we're thinking about spectrally low energy, then we can do a multipole expansion, okay? So when we write this in terms of a multipole expansion, then this part, this thing over here, becomes where this is the dipole moment operator of the charge distribution. And this is the electric field at the center of mass of the charge distribution, the center of the charge distribution. Okay, so this is the first multipole. I'm assuming a neutral charge distribution, otherwise I would have to think about what the monopole interaction is with the scalar potential, but if this is a neutral charge distribution like a neutral atom, of course I might have an ion, but let's just think about neutral charge distributions, then this is dw. Yeah?
So, in the first part that
Yeah.
you are quantizing space, but then,
I'm not quantizing space, I'm quantizing the position of the electron. So I want to be very clear, this whole story always is the motor, when we talk about position number, this is the position of the electron, not the value of space-time itself. Okay, space-time itself is a parameter. We're not quantizing. We have to quantize the metric. That's quantum gravity. When we write R, this is the observable of the position of the electron, not the position in space. Okay, so there's a distinction. I want to be clear about this whole story about this because it's been confusing. Okay, this is the position of the electron and the momentum of the electron, like we always do in quantum mechanics. Great. Okay, so with that said, this part is like the thing that gives rise to the energy levels of the atom. Like we would solve the hydrogen atom. We'd have a proton, we have an electron, we'd have the kinetic energy of each one of the guys. We go to the relative coordinates, we quantize it, and we get a set of energy levels, okay? So this part, which I'll call the Hamiltonian of the atom, this part is now the interaction between the atom and the field, which we are taking in the dipole approximation as the dominant term. Then the Hamiltonian of the atom is generally a sum over all the energy levels of the atom with some energy eigenvalues, these are the bound states, plus we might have some continuum states with some density of states. The unbound states. That's the most general form. If I were to diagonalize the Hamiltonian, it has energy eigenstates. It has bound states and unbound states, okay? Right. Now, again, we're going to, as we did when we talked about our interaction with a classical monochromatic field, we went to a two-level atom where we chose two levels. One we called the ground state. It might be the actual ground state or some other state that we're going to just say is a lower energy. And one other energy level we're going to call the excited state. So this is picking out two particular discrete energy levels. This is our approximation of a two-level atom. Yeah?
Which particular D is that?
That's the energy eigen. These are the energy eigenvalues. I'm summing over all of them or integrating over them.
And the cursive D?
It's the density of states.
Okay.
So the point here is that if I wanted to be very, precise about it, the spectrum of the atom has discrete energy levels and unbound states. This would really be the Hamiltonian of the atom that are just diagonalizing this, okay, as we do, for example, for hydrogen, okay? But what I'm saying is that we're going to restrict our attention to two specific energy levels. One might be the ground state and some particular excited state. Could be any other two levels that I care about. One of the lower one I'll call the ground state, although it's not the actual ground state, which is dipole allowed. So there is a dipole matrix element between this, right? The dipole matrix element here, the D here is, the sum over all the electron positions, and I take the matrix element of that. That's my expected dipole moment. Okay? Now, when we talked about this in the context of the classical field, like a laser driving a two-level system, this kind of made sense. We argued that we can restrict our attention to these two levels and only these two levels because we said, well, I'm in the ground state and I'm going to put on, 859 nanometer laser on my cesium atom, and it's only going to couple to the first excited state, and it's so far off resonance from all the other ones that if I start in the ground state, I only ever get population in the other states, so I can forget about the rest, okay? So in this case, we don't, at the moment, have any field on, so why we can restrict our attention to only two levels is not well justified. I have to come back to that to see, what is that? What happened to the rest of those levels? But for the moment, bear with me, all right? So, very good. So, let's again, so now my dipole operator, when restricted to this, and I'm going to assume that these are states with well-defined parity, so that the dipole matrix element of, or the expected value of the dipole in either the ground state or the excited state is 0, okay, so they have no mean dipole. Let's just say the charge is not displaced, right? They have their eigenstates of parity is one way of saying that, as we discussed earlier. Then under that, as we did when we talked about this classically, the dipole operator, when restricted to the two-dimensional subspace, takes the form dE EG plus D GE GE, right? Everyone clear on that? Because when we restrict this to this and we just put in a complete set of states, it only has off-diagonal coupling. It only couples the diagonal element is 0. Yeah?
That capital D isn't displacement. It's not.
Where? This D?
Yeah.
No, I'm sorry. This was the density of states.
Sorry.
I didn't want to make this confusing. I just wanted to give you the basic, these details weren't important. Just, there's lots of levels. Some of them are unbound, some of them are bound. We're going to just restrict ourselves to 2. The details of this are not important. Yeah?
atom interaction Hamiltonian?
Yes.
Does that include just the dipole moment or all?
No, just the dipole moment. So we're making the approximation that, which is a great approximation, which is that the size of the atom is tiny compared to the wavelength of the radiation. And under that approximation, the interaction Hamiltonian can be written in terms of multipolar expansion, where the absolutely dominant term is the electric dipole, assuming it's neutral. Okay? If it wasn't dipole, if these two levels were not dipole allowed, then I might want to think about higher order multipoles, like a quadrupole. Oh, everyone loves the quadrupole. But we're not. Okay. Good. All right, so this is my electric dipole operator. And so, and E, the electric field operator, okay, I should also say, in principle, the center of mass position of the atom should also be quantized. I could think about an atom whose motion I think about more in its wave-like nature than its particle-like nature. And in fact, if I cool an atom down sufficiently low so its de Broglie wavelength is very long, then I do have to do that. And we do it all the time. They're called laser-cooled atoms. And we think about the quantized motion. But for the moment, I'm not going to think, I'm just going to think about the center of mass position as a classical parameter, okay? Which is to say, I'm not worrying about the quantum nature of the motion of the atom, only the quantum nature of the electron bound to the nucleus. Okay, so with that said, my electric field operator at the position is the sum of the positive and negative frequency components. Where the positive frequency component is the sum over the modes 2 pi h bar omega times some mode function, which is a classical mode function, e to the I, k x, that depends on k and u. So this could be, for example, I'm sorry, I've already written that out, sorry. That's the annihilation operator. The mode operator could be, for example, a plane wave, quantized in the volume. So these were our kinds of modes we looked at with a polarization and a plane wave in a quantization volume with periodic boundary conditions. So that's our kind of pseudo free space quantization where we just put on fake boundary conditions. Or we could think about, you know, a cavity mode. So we might think about atoms in a cavity, as we will in just a little bit. And then these are not plane waves, but they're Hermite Gaussians, TEM00s with, you know, plane waves. Yeah?
The mode operator is only an operator if we quantize the center of mass, right?
No. Oh, you mean the mode itself? The mode is a classical field.
Okay, that's sort of
Yeah,
the arrows
yeah,
going.
yeah. Yeah, I'm sorry. The mode, this guy I'm saying is, these are our classical functions. Now, they represent, as we did, quantizing the field in terms of normal modes. Now, if I have an atom that is located at some position in space, and I'm interested in that degree of freedom, then this will depend on that center of mass, and I would put a hat on that. That would be associated with, you know, the motion of the atom at that point. Okay, but at the moment, we're not worrying about the motion of the atom. Okay, and E dagger of this is E minus. So it has the other terms. Now I lost that board. I'll leave this stuff up here for now. Okay? So let's write down now d dot e. These guys. So d dot e is going to be minus DEG, and I'm going to call, as we use the Pauli operators, where spin down is the ground state and spin up is the excited state in my pseudo-spin representation. So this is my sigma plus, and this is my sigma minus.
There's no state here yet, this is just operators?
This is just a Hamiltonian,
Okay.
right? So this is my atom field Hamiltonian. It's my interaction Hamiltonian. This is the Hamiltonian that describes that interaction. Okay. Very good. And so let's write all of this out. Okay, so now what I want to do, just to get a sense of things, I want to go to the interaction picture. So in the interaction picture, this is the interaction Hamiltonian is a function of time, where it's a function of time evolving according to the free field Hamiltonian. Okay, so this is my field Hamiltonian, where this is my free evolution without interaction. So this thing is now a function of time, this is a function of time, and these guys are functions of time.
So is the u naught of t like e to the I t h a? Like just the atom Hamiltonian?
Both the atom and the field. This is e to the minus I h atom plus h field without the interaction. That's what that is. And so in that case, what we know in the interaction picture, the annihilation operator evolves like e to the kt. Yeah.
Is it minus I over h bar?
Yeah, h bar when I'm happy, when I feel like it. Sometimes I don't feel like it. Yeah,
Just because it's kind of hard to read from here, those are R's.
they are. Sorry, I'll try to write a little more clearly. Sorry. My handwriting has degraded over time. It's very unfortunate.
You should see mine.
Yes, well, yeah. Anyway, all right. So that's the free evolution of the mode, and the free evolution of this is, e to the minus e t excited, and then e to the minus I is a plus because it's on the other side. So that's e to the minus I. I'll be good and put in my h bars. Is e to the minus I e g. No, this is the dagger on this side. That backwards. The dagger has the plus. The other one has the minus. Now it's right. Okay. So that's the time evolution of this. So let's write this out then. The atom field interaction in the interaction picture is equal to, I'm going to write it all out in the following way. Minus k, sum over k mu, something I'm going to call let's write it out. Actually, I'll write it like this. I'll define this in a moment, this constant G. All right, so I have these terms with the A dagger. Okay, so I have these four terms where I've defined h bar times this constant g as minus d dot e dotted into the polarization e to the times the square root of 2 pi h bar omega over the volume times the phase at the position of the electron. So I'm assuming, it doesn't really matter, these could be, this thing could generally be, I can write this generally as minus d dot e dotted into u at the position of the electron square root of 2 pi h bar omega. Okay? So let me state what these things are, all these are, when I'll come to questions in a moment. So this constant, G, is a coupling of the dipole moment to effectively the electric field of one photon. Okay? The electric field of one photon has a strength that depends on the mode function and in these units. So this is a coupling constant that couples the atom to the field through the dipole moment, the electric field. And then I have four terms. The four terms came from this with this, and this with that, and that with that. All four terms, the E plus and E minus, all four terms gave me all these things. Okay? Yes, Don, you had a question?
Yeah, so those are two separate sums, right? I'm supposed to read that big dash at the end as the parenthesis closing each of them?
Yeah, I know. They should be, I should be more careful. There's this, then this.
Okay.
So I have these four terms. Okay. And those four terms came from just multiplying this out. All right, let's look at what these terms are. Yeah, Dave.
Was the subscript in the omega under the square root?
So K. Omegas are labeled by K. Okay, so let's take a look at these terms. I see that some of them have the possibility of resonance. Okay, that is to say, there exist some modes for which the frequency is equal to or very close to the Bohr frequency. Omega Eg is the energy difference between the excited state and the ground state over h bar, what we call the Bohr frequency. And so these terms have resonance, whereas these terms are what we call anti-resonant. There's no way for this to be zero. These are extremely fast oscillating terms. And when we were to, if we were to look at the dynamics of the system, things that are oscillating huge at huge rates compared to these rates, assuming this rate is absolutely tiny compared to this, that rapidly oscillating thing is going to do almost nothing. Okay? Only terms that can contribute are the things where this becomes small enough that this becomes on the order of this or zero. Okay? So when this coupling constant is sufficiently small, the anti-resonance terms are negligible. Okay? Now, but I want to just look at this a little bit more closely to try to understand what do these terms contribute to and what is their physical interpretation. So let's look at then each of these four terms in succession. What does this represent? This represents annihilation of a photon, absorption of a photon, at the same time as I raise the atom. I go from the ground state to excited state. So we would call that absorption, right? So the absorption happens at the same time as the atom goes from the ground state to the excited state. So we've excited the atom by absorbing a photon. This term is the reverse. This term, a photon is created, let's say it is emitted into the field, and it's commensurate with the atom going down, lowering from the excited state to the ground state. That sounds normal. But what about these other terms? I mean, they're there. They correspond to something that seems absolutely insane, right? In this case, a photon is absorbed, but the atom goes from the excited state to the ground state. And this is the reverse. This is a term in which an atom is emitted, but in the same process, let's see, this guy should be a plus, that doesn't make sense, right? That's the conjugate one, right? And now I raise the atom, right? In commensurate with, so these terms seem really weird, and they seem completely unphysical. Are they even physically there? Yes. And what do they correspond to? So part of this has to do with what we think about absorption emission. And so I'm going to be super fancy. Okay, fix my hair. All right. So let's write Feynman diagrams. I mean, Feynman diagrams are written in high energy physics in exactly this way. You write down the perturbation theory and you think different level. Each term in a sort of perturbative expansion is a diagram. So I can think about each thing as a fundamental process. So here's an example. This kind of process, I'm going to draw the diagrams in a kind of, ready to say, okay, I'm going to say the ground state is a skinny line and the excited state is a thick line. Rather than electrons and positrons, I'm going to have ground states and excited states, okay? And then I can have a photon being absorbed, which I'll draw as we do, typically called in QED the photon gamma. So this is the process by which the atom goes from the excited state to the ground state, absorbing a photon. That was the term that was annihilating the photon and raising the atom. Okay, that was that term, right? That sounds fine. And then we have the conjugate case where I started in the excited state, I went to the ground state, and in the process emitted a photon. That was that, right? But what about this other term, or these other two terms? Well, let's look at that. That corresponds to the case where, let's look at the case where let's start with this one, okay? Let's say that I go from the ground state to the excited state, but in the process, I emit a photon. Okay? Or the other way around. I lower the atom, but absorb a photon. Okay. These processes are, in the jargon of hydrogen, off the mass shell. Very fancy way of saying that. What I'm trying to say is they don't conserve energy, okay? At least there's no way for me in first order to start with a state that had the ground state and end in this state. That doesn't exist to first order because it can't conserve energy. 1 second, Nate, I'll get your question. But who said this is just a first order, these are one Feynman diagrams that constitute one order of perturbation theory. We could go to second order in perturbation theory. And in second order in perturbation theory, I can combine any of these two diagrams together. So here's an interesting diagram. Okay, so in this case, I combined these two diagrams in succession. First this, then this. I started in the ground state. I emitted a photon, went to the excited state, but then came back to the ground state, and at the end of the day, energy is conserved. Intermediately, energy is not conserved on this picture, and we call this a virtual photon. Nate, you had a question, so what?
Should that be sigma plus?
This should be sigma plus. Yes, indeed. Thank you. Excuse me. Keep doing that. 'Cause, yeah.
Is that kind of virtual photon, could you like also figure out whether or not that could exist by the delta E, delta T relation? I've heard people mention things about it.
Right. So So there's all kinds of. Okay, you ready? I'm waving my hands at you. Loosey-goosey things. People say, "Oh, we can do that because we're only there for a short time, and the time energy uncertainty principle says I can emit a virtual particle for some amount of time as long as that time is short, and therefore the energy uncertainty is high." What I would say is the following. None of these states are energy eigenstates of the system. The system has an uncertain energy. If I'm looking at it in this basis, these states are not the energy eigenstates. The energy eigenstates are the energy eigenstates of the whole Hamiltonian. If we choose to look at it in terms of this basis, we're going to have energy uncertainty because because we're not in an energy eigenstate. And so this kind of evolution is a perfectly good kind of evolution. It's very similar to the idea that even though if I thought about my laser and I put on a real Rabi frequency, I have some probability. I mean, people start saying, "Oh, I got to a virtual level." Well, no, it's just that this is not neither of these are an energy eigenstate of the system, so there's some probability amplitude to be there, and there's a probability amplitude for having a photon in the system. Now, this kind of diagram, the way that it plays a role, as I say, it doesn't play a role in first order, but it does play a role in higher orders. And what it does effectively is because, and this is what I wanted to say, because the atom is interacting with the field, the eigenstates of the atom are not what they used to be. There's the bare states of the atom in the absence of its interaction with the field, but because it's coupled to the field, the energy levels of the atom are now different. And they're shifted. This diagram corresponds to a shift. If we were to do perturbation theory, if I were to ask how is the energy of the ground state of the electron perturbed due to its coupled to the vacuum, I would have this term. I could write down all the Feynman diagrams, and this would be a contribution to that. And what we say then is that this whole thing leads to a sort of new ground state which is renormalized. which is basically to say this perturbation theory. So what we call the ground state of the atom in the absence of the field is no longer the ground state. It's shifted. And this contribution from the vacuum photons gives rise to something called known as the Lamb shift. After Willis Lamb. So Willis Lamb calculated this in QED. Now, but we would not get the Lamb shift correct in the dipole approximation, because gamma ray photons contribute to the Lamb shift. By making the multipole approximation, we're not going to get the Lamb shift right. But there is a contribution to that from the low energy photons. This is a contribution to the Lamb shift. Yeah?
So then the recaptured photon that's recaptured by the atom, is this resonant with the dressed atomic states now?
The whole thing is the dressed atomic state.
Yeah.
This whole thing is the new ground state.
Yeah.
These kinds of, in the same way we think about the electron, moving through the vacuum, it's really dressed by all of its, positrons popping in and out of space. And what we call the mass of the electron is the thing through all those virtual processes. But in quantum optics, we're not going to do all that mess. We're just going to say, okay, fine. There's a new ground state, and whatever that is, it's taken into account by this. Okay, and so we're not going to include these terms for these two reasons. We're not going to include the anti-resonant terms for two reasons. One is, so first order perturbation, they are anti-resonant and they contribute almost nothing to the probability of being absorbed because they're so far off resonance, okay? These terms oscillate at huge rates. Secondly, yes, they contribute to in second order, but that's, we say we renormalize and the energy of the ground state is now changed, okay? So neglecting those terms is exactly what we did also in the classical case. We didn't have all this fanciness of Lamb shifts but we had the same exact thing, and that's what we called the rotating wave approximation. It's exactly the same thing. We neglected those counter-rotating terms. We argued they were highly oscillating. We argued that in terms of how a precessing top was resonant with a co-rotating torque or a counter-rotating torque, and that gave rise to what we call the rotating. But it is the same thing. In this quantum picture, we can see they correspond to these virtual processes. Yeah?
So is removing the anti-resonant terms equivalent to saying we're going to ignore the negative frequency component?
No, it is not.
Oh.
These are the negative frequency
Oh, I
components.
see. Okay.
It's just that we have the positive frequency component associated with absorption and the negative frequency component associated with emission.
I see.
So we have both absorption and emission, but we don't have this with
I
this.
see. Okay.
Right. Very good. Thank you for the question. All right. So with that said, we have our what we call the quantum optics atom field Hamiltonian.
It's the same as like Jaynes-Cummings Hamiltonian.
That's what we're about to write down. We're not exactly the same. We'll explain that in one moment.
Oh, thank
So my Hamiltonian here is, we got my two-level atom, and my two-level atom, so I'm gonna say the energy of the ground state I'm gonna call 0, and then the energy of the excited state is that. So this is h bar omega Eg times the projection on the excited state, which I can write as sigma plus times sigma minus. It's the same thing. So that's the whole atom Hamiltonian is just this now. We have the Hamiltonian of the field, which is just the harmonic oscillator. And then the atom field Hamiltonian yeah.
Should one of those in the middle?
Oh yeah, they should not have a dagger. I don't know where my head is, but it's crazy.
So this is our first order.
So this is first. I mean, this includes all orders of perturbation theory.
Okay.
It includes all orders of perturbation theory because the terms, because it. I mean, the only thing we neglected in this case. So I went back to the. This is in the Schrodinger picture. I put back in the free evolution. What I did is I neglected the counter-rotating terms. The counter-rotating terms are there, but they're going to contribute only to a renormalization of the energies. So I lump that in renormalization, and I forget any of their effect. But this is not a first-order perturbation theory. This has all orders. But it has a variety of approximations. We had the two-level atom. Come back to that. We have the dipole approximation and the rotating wave approximation. All of that gave us this. Okay. Excellent. Okay. So now I want to turn my attention to the simplest possible problem in the world associated with an atom interacting with the quantized field, is to think about the case of so this would be the situation where we might have, this is what's called cavity QED, cavity quantum electrodynamics, okay? Where we imagine, for example, this could be an optical case. I have a Fabry-Perot cavity, okay? My Fabry-Perot cavity has modes. Those modes have to do with the distance between the cavity and the curvature of the mirror. And if I had a perfect cavity with infinite reflectivity, no absorption in the cavity mirrors, no leakage of cavity, then there are a discrete set of cavity modes. Those are discrete set ones that fit the boundary conditions. And we were to look at the spectrum, we would see, you know, there's a bunch of longitudinal modes and transverse modes around them, and there's the discrete modes that fit in the cavity, right? These have certain free spectral range, whatever the hell that means, and you know, but I'm not for the moment assuming anything about them having leaky. So these are my cavities, and inside that cavity, I'm going to trap an atom. Okay? It's sitting somewhere at some position, and I'm going to choose this in such a way that, so these are all my cavity modes. There's one particular mode of the cavity, I'm going to call it omega sub c. This is my cavity mode. A particular cavity mode might be the one I drew, such that this is chosen to be very close to the resonance frequency of the atom. Okay, so the atom might be my favorite atom, cesium, okay? And and you know, the first excited state, the 152 nanometers, and I'm going to choose that there's some mode that's almost exactly at that frequency. It might be off by a megahertz out of 10 to the third terahertz, okay? So there's some one mode, the mode that is very close to the atom. And all of these other guys are way off resonance, okay? In that case, all these way off resonant modes are irrelevant. Only one mode, this one cavity mode, couples to the atom at all. If the atom starts in the ground state, there's no photons at any other frequencies that can drive it, okay? So in that case, my two-level atom approximation is again a good approximation because this one mode is near resonance with the atom, okay? And so in that situation, I can turn this Hamiltonian to say, well, there's only one mode, I'm not even gonna put a label on it. That's the one mode, that one cavity mode. There's a creation and annihilation operator associated with that mode. And that's the energy of the photons in that mode. And then my Hamiltonian over here is H bar G, A sigma plus A dagger sigma minus. Okay, where G, H bar G, is equal to minus D dot, the mode function at the position of the atom, times the square root of 2 pi H bar omega C. Okay, so let me write it again on this board. So in this situation where I have well-defined modes of the cavity that are well separated and only one of them has a frequency that is near the resonance of my two-level atom, I have what's known as the Jaynes-Cummings model. What's that? Cummings. Single mode of a cavity interacting with a two-level atom. The Hamiltonian that describes that is this. This is the energy of the atom, this is the energy of the field or the photons, and this is the interaction energy. You can make it complex if I like.
Is this to a specific order in perturbation theory?
No.
No.
Nope, we have not made perturbation theory at all. What have we perturbed? We have not made perturbation theory at all. All we neglected was the counter-rotating terms. We haven't done perturbation theory. Yeah.
Saying we only have that one mode, that gets rid of all the K's, right? What about the mu's for the
Yeah, but the mu is chosen. There's only one polarization that couples to a particular, right? If I have multiple degeneracies, there's only one polarization. So both its spatial mode and its polarization, there's only one mode that couples the ground state to that excited state. Great. So this is what's known as the Jaynes-Cummings model. The Jaynes-Cummings model was written down by Jaynes and Cummings in 1964 as a kind of curiosity, I think. You know, just sort of, you know, what is, I mean, so I don't know if you guys know who Ed Jaynes was. Ed Jaynes is very famous physicist who ultimately became very famous for his he's a really founding father of information, one of the founding fathers of information physics, connecting the theory, information theory to physics, and in particular, he was thinking about in the context of thermodynamics and how statistical physics should be thought about from a Bayesian perspective. I should read his work afterwards. But he was also interested in the nature, quantum nature of the field, and he played around with this model with, where the hell Cummings was. I'm sure Cummings was a great guy too. I assume he was a guy, I don't really know that. But anyway, you know, and it's so interesting to me. So this is a very, to me, it's kind of a lot of the story of how physics is done. Sometimes we do physics to create, you can think about this as a complete toy model of quantum electrodynamics. The simplest toy model, it's the spherical cow on steroids, right? No udders at all. And this is, you know, one atom, a two-level atom, one mode, you know, what is the property? What's the toy model of it? You know, I mean, and its properties were studied, as we'll see, you know, in some very famous experiments that ultimately won the Nobel Prize by Sir Desroches in 2012. You can review some of his studies, some of his experiments for homework in your final homework this semester. Because it's a beautiful model of thinking about atom field interactions. But you know, it was kind of wild. I mean, come on, anybody, you guys can diagonalize this Hamiltonian. This is a trivial model. I mean, seems like a complete sort of uninteresting toy that doesn't tell us anything about fundamental physics. But there are a few different things I would say about the Jaynes-Cummings model and how this is done. One is sometimes getting rid of the complexity and making it as simple as possible allows you to focus in to what's really important. And the whole notion of how atom field coherence is controlled and how it's lost and decoherence was understood in studying the Jaynes-Cummings model, okay? The other thing I would say about this and the way physics is done is sometimes we say, okay, here's a toy model that we use to try to understand the more complex universe. But sometimes we say it the opposite way. Well, now that we have this toy model, maybe this is not the way the universe works, but who cares about this stinking universe? I'm gonna make my own universe. I'm gonna make a system that actually is well described by this toy model. Because then I know it exactly and I can manipulate it and control it into such an umpteenth degree that I can do things in the quantum world that the universe doesn't do. And that's what we do. In fact, the entirety of almost all quantum computing platforms make use of the Jaynes-Cummings. They're all based on the Jaynes-Cummings model. This is how superconducting quantum computers do. They work based on our ability to manipulate things based on the Jaynes-Cummings model. So understanding the Jaynes-Cummings model became incredibly important. And you know, all the condensed matter physicists said, oh my God, this is the most trivial thing. Where's my partition function? Said, oh my God, we got to learn some quantum optics. And they did. And they created circuit QED, and we'll come back to that in a moment. All right, so I said this thing can be diagonalized. Of course, anything can be diagonalized in principle, but in an infinite dimensional system, it's impossible to diagonalize. I mean, I can't write down the matrix. But this thing has conserved quantities. Because we've made the rotating wave approximation, if we absorb a photon, then we lower the atom and vice versa. So the total number of excitations in the system is conserved. Yeah?
Can we use this to describe a laser, or do we have to change it?
There's aspects of this. I mean, the thing about a laser is that a laser ultimately is multi-mode, and you know, and we don't really also have a two-level system. We have to pump the system in order to have population inversion. So there are aspects of this, the essence of this. I would say we could go back to, you know, our write it down. Here's a quantum optical Hamiltonian. Oh, here it is. This, if we started more generally than the laser. The quantum theory of the laser, which Lamb also worked on, starts here. Yeah.
Does this specifically have to be for cavity, or can I, for example, simulate a monochromatic single photon laser?
The question of a mode becomes important. If I have a temporal mode, it's not going to interact sufficiently long with the atom to be able to do what I want. So I really want a standing wave, and I really want a cavity. Now, it doesn't have to be a photon. It can be a phonon. So the Jaynes-Cummings model also describes, for example, the coupling of, say, a two-level ion coupled to its vibrational motion in an ion trap. So that's also described by the Jaynes-Cummings model. This is something called a spin boson model, because we're coupling like a two-level atom, or a spin to one bosonic mode. Okay, let's diagonalize this thing. Okay, so firstly, let me define n as the number of photons plus whether the atom is excited in. All right, so this is the number in the excited state, the probability of being in the excited state. This is the projector in the excited state. All right, so I claim this thing commutes with the Hamiltonian. It's easy enough to check that. I'll leave it to you to do that commutation. But it's intuitively obvious, because what this is saying is if I have some number of photons, so let's think about a basis of the Hilbert space. That basis, what is the Hilbert space we're talking about? The Hilbert space is the Hilbert space associated with the atom and the field. So my Hilbert space is the tensor product of the Hilbert space of the field. This is not the Hamiltonian, it's Hilbert space, and the Hilbert space of the atom, right? A basis of the field, for example, are Fock states. And the basis for the atom are, say, the ground excited state. Okay? So a basis for the Hilbert space involves either the atom in the ground state with n photons or the excited state with n photons, summed over with n goes from 0 to infinity. Okay, that's a basis of the Hilbert space. Now, what is true is that this Hamiltonian is block diagonal in sectors that have the same number of excitations. So I can think about if I have no excitations, there's only one state, the ground state, and no photons. That has no excitations. If I have one excitation, what states can I have? And how many photons? Because I have to think about the excitation could be in the atom, or they can be in the
0 or 1.
So what are the states which of these states?
Ground 1, excited 0.
Excellent. So these two states have one excitation. Either the excitation is in the field or it's in the atom, right? 1 second, I'll get to this. What about if I have n equals 2? What are the possible states?
Being ground with both photons?
If we're n equals 2.
G2V1.
It's down to excited 1, etc. And if I have n excitations, I have the ground with n and the E with n minus 1. For n greater than 0. Yes, Donald?
Saying is block diagonal is equivalent to saying that excitations are conserved, right?
That's correct. So what that means is if I write the Jaynes-Cummings Hamiltonian in this basis, it only has off-diagonal elements within a given block. There's no way to couple the n=1 sector to the n=0 sector, right? Because n is conserved. So if I were to write the matrix in an ordered basis, I'll have zeros everywhere here. This is a 1 by 1, and every one of the rest of these guys is 2 by 2. This is n=0. That only is this state. Then I have n=1, n=2, dot, dot, dot. Everyone clear on that? So the Hamiltonian block diagonalizes into a bunch of 2 by 2 blocks. Each one of these 2 by 2 blocks correspond to some number of excitations in the system. This block has 1 excitation, it couples these 2 states. This one has 2 excitation, it couples these 2 states. And so all we need to do to diagonalize the Hamiltonian is diagonalize each of these blocks. Yes?
Because these, I'm assuming, are indistinguishable, will we get coherent stuff?
Well, what do we mean by indistinguishable?
Like, the states, for example, E1, you just know that one's in the ground and one's in excited, but you don't know which one is which.
There's only one photon and one atom. So the atom and the photon are distinguishable degrees of freedom. So there is going to be coherence, but it's not the coherence associated with indistinguishability. Indistinguishability is associated with excitations that can't be distinguished. We can tell whether the excitation's in the atom or in the photon because they're different physical things, and we could do a measurement that could tell the difference between them.
Like for the G2 state in the n=2 subspace.
Yeah.
In theory, there are 2 photons, right?
There are 2 photons.
And those would be indistinguishable.
They are.
But we don't really care.
But exactly. That is what it is. Now, I want to make one other small point, that this is a kind of complete annoyance, and I didn't make this one. G means 2 completely different things in the standard way we now write the Jaynes-Cummings model. G represents whether I'm in the excited state or the ground state, and it's also the coupling constant. Okay? They have nothing to do with one another. They both use the term G. You just have to know by the context. Okay? It's like the Torah without the vowels. You just have to know. Okay? It's just context. Okay.
This is the context.
Right? So you just have to pay attention to that. All right. So let's diagonalize one of these blocks, right? It doesn't matter which one, they're all. So let's look at the nth block. The Hamiltonian in the nth block, well, I need to know what the diagonal matrix elements are and the off-diagonal matrix elements, okay? So now, because this is each one of these blocks is a 2-level system, it's a qubit again. It's a different qubit, but not the one. It's got both atom character and photon character, but it is a 2-level system, and every 2-level system is a qubit. So I'm going to have new kinds of Paulis, right? So I'll call spin up excited with n, and spin down the ground with n-1. Okay? So let's think about what our Hamiltonian is in the spaces.
It should be n-1 before, because if you're in the excited state, you have n-1.
Yeah.
It should be flipped. Should be, you are right. n-1 and gn. Absolutely. Very good. So the let's call this down to the n, so that we'll remember that we have n excitations in this sector, okay? So in this case, what I have is h bar Eg that has one excitation in the excited state and n minus one cavity, right? That's the diagonal matrix element of that. And the down part of this qubit has nothing here and n here. Okay. So this thing has, if I think about this, minus h bar delta plus n c, where delta is the energy of the photon in the cavity minus the atomic resonance frequency. Okay? Bless you. What about the off-diagonal matrix elements? In this problem? Well, the off-diagonal amounts associated with this is a raising, so this is going to be h bar g times, I'll say, e with n minus 1, a sigma plus g n. Okay. How do I calculate that matrix element? Well, this is a tensor product. So this thing over here is this times that. And this is 1. And what is this? Square root of n. Okay? So this is equal to h bar times the square root of n times g. Okay? And the other one's the complex conjugate. I'm going to take g to be real because in a cavity mode, when I have a standing wave, it's a real number. It's not. Okay?
This is the expectation of spin up. That specific.
That's matrix,
Yeah.
that matrix element. Okay? So what we have thus is our Hamiltonian looks like this. This block looks like this. That's the Deutsch notation, is represented by this matrix in the basis of spin up and spin down being these states. You with me? How do you diagonalize that matrix? You should be able to just do it by eye, because why?
Because
It's a 2 by 2 and you write in terms of Pauli's, right? And so what this thing is equal to is minus h bar omega over 2 plus n times h bar times the identity minus sigma 3 plus, I guess this should have been h bar. So instead of calling them sigma x, sigma y, sigma z, I'm going to call them sigma 1, sigma 2, and sigma 3, because there's too many x, y's, and z's. What are the eigenvalues of this matrix? Along, right, that's the eigenvectors. What about the eigenvalues? right, the magnitude of that square. So the eigenvalues we have are minus h bar delta over 2 plus n h bar omega c plus or minus h bar omega over 2, the square root of 2g squared plus delta squared. I'm sorry. N times 2g squared plus delta squared. Okay, come back to the eigenvector, but I just want to conclude. Let's just look at what now the spectrum is. Let's look at what it looks like. And let's particularly take the case that I'm on resonance. Okay? So if I had no interactions, if G were 0, what would I have? I would have the following spectrum. Where each one of these guys is doubly degenerate. Each one of these guys is doubly degenerate. It has G with N or E with N minus 1. Those two states are degenerate. They're doubly degenerate if I'm on resonant. Okay? And they're spaced by the cavity. Every time I go up by one rung on the ladder, I go up by h bar omega c. Yes?
And it's always uncertain where the n is between the ground state.
Right now, I'm just saying, what is the spectrum? What are the energy eigenvalues, and what are the energy eigenvectors? I'm not saying anything about the state yet. I'm just looking at what is the spectrum, what are the eigenstates of the system. We'll come back to the dynamics in a moment. So now, if I turn on G, what happens? Well, this state stays the same, but what happens to this state? It splits. It splits into two states that are split by 2g, right? One goes up by 2g over 2, and the other one goes down by 2g over 2. We have the plus with 1 and the minus with 1. Okay? And what about this state? It splits too, but it splits by a little bit more. It splits by 2 root 2g. I have the one with plus with 2. And up here, it splits even more. This has n times, it has square root of n 2g split. Okay. This spectrum is known as the Jaynes-Cummings ladder. It's a nonlinear energy level splitting. In the absence of interactions, this was a harmonic ladder, equally split. But when I turn on these interactions, I get these splittings with a nonlinearity that depends on the square root of the number of excitations. Donald first, and then Nate, and then we'll call it
You
quits.
ever have it where they split so far that they cross over?
No.
Okay.
No, because this is a terahertz, or 10 to the, and this is, megahertz, whatever. So no, we don't worry about that. These things are so far apart, but you're right, in principle they could, then we'd have to think about these guys crossing. So this is interesting. This is a beautiful spectrum, and we'll talk about this. So I just to say one last thing. Suppose I were to start the system in the ground state with one photon. Okay, that state's not an eigenstate of the Hamiltonian. The eigenstates of the Hamiltonian are the superpositions of these two. They have both these states. So what's going to happen to that system? It's going to Rabi oscillate. It's going to Rabi oscillate between these states at a Rabi frequency that's given by this. So I will go, for example, from the state with the ground with one photon and back and forth. That's known as a vacuum Rabi oscillation. It really is a one photon Rabi oscillation, but people call it a vacuum Rabi because it goes from excited with one photon in it, it gets absorbed and then re-emitted, and then absorbed and then re-emitted, and then absorbed and then re-emitted. But it does so in a coherent manner, so that it is going from a superposition from the ground state to an intermediate state, which is a superposition of these two. Back to that. It's not a rate equation where there's stimulated absorption emission. It is a coherent rotation on the block sphere between these states. But we have to get out of here. I'm going to take other questions outside, but we'll continue this discussion.
Jaynes-Cummings model is basically just a Hamiltonian and it's a